Alright, so I'm gonna try this again. Um, problem, section 2.4, problem 8. Um, the cylindrical buoy of diameter 60 centimeters in figure 43 is floating in water with its axis vertical. When depressed downward in the water and released, it vibrates with period 2 seconds. What is its weight? So we have here that my double prime plus ky equals 0. And the force equals mass times acceleration, which is mass times y double prime. So we have the my double prime term, which is negative 9.81 times 0.3 meters squared times pi y. So this is pi r squared. Y is the displacement, and this is the force of gravity, obviously. So, if you rearrange this equation, we can solve for k to get negative y double prime over y. And, oh, these are just the two forces that are acting on the thing. So the buoyancy force and then the my double prime, which is the force of pushing down. So we have k equals negative my double prime over y. And if we plug this in, there's a y on the top and the bottom. So it ends up that the y cancels out, and it doesn't matter how much it is displaced because of the y double prime term being over this. So I think that's what you were asking me for the most part, is why the displacement didn't matter. And you can see here that this force above the y right here just cancels out. So from there, you can plug those numbers in to get k of 2.77. Then we have omega equals square root of k over m, and omega also equals 2 pi over t. We can square 2 pi over t and k over m to get 2 pi squared over t squared equals k over m. So then you can get m equals kt squared over 2 pi squared. We know that t is 2. Solve for m, plug in the k, and we get that the mass is 0.281 kilograms.